Okay, so let's do a quick review of what we know about polynomial time reductions. So we are interested in efficient algorithm, and in our language, efficient algorithm means polynomial time. And to find, because we're interested only in efficient algorithm, we're interested only in polynomial time reductions, which preserve polynomiality. And reduction that takes longer are not useful, like the reduction we just saw for NFA universality. And now if we have polynomial time reduction from a problem X into a problem Y, and we have a polynomial time solver for problem Y, this is the reduction, this is the solver, then we can solve the whole problem in polynomial time. And we designate this fact that we have a polynomial time reduction between X and Y by saying X is smaller equals subscript P from Y. Okay. Right, and the important thing for our purposes is the proposition that says that if X is polynomially reducible to Y, and that polynomial time algorithm to Y, then there is a polynomial algorithm for X. Right, and such a reduction is called a CARP reductions. Here we require that we map an instance to an instance. It's a single shot reduction, and it's called a CARP reduction. Okay, let's do a review question. So we have problems X and Y. By the way, I should say about reductions, the most common mistake with reductions is that you're doing the reduction from the wrong direction. So you always have to think very carefully, am I reducing this problem to this problem? Is the reduction done in the right direction? This is like the universal mistake that students make about reduction, and frankly, I also make this mistake sometimes. So we have two problems, X and Y, decision problems, such that X can be solved in polynomial time, and we have a polynomial reduction from X into Y. What does it imply? So we have 5 options. Y can be solved in polynomial time. Y cannot be solved in polynomial time. If Y is hard, then X is also hard. None of the above, and all of the above. Okay, so because of the liar paradox, it definitely cannot be E, because that would contradict D, which is none of the above. So we can remove E. And if you look at this, right, then you can, you have to think about it a bit, right? So all we know is that X is easy, and there is a reduction in polynomial time to Y, right? But Y, we don't know what it is, right? Now, one of the classical trick is to, essentially all you're saying, as the notation suggests, all we know is that X is smaller or equal than Y, and we know something about the value of X. That doesn't say anything about the value of Y. So if you look at the notation, it looks like we know nothing about Y, and that is indeed the correct answer. And such, it's not true that Y can be solved in polynomial time, because Y can be a very hard problem. In fact, the classical shticks is to take a polynomial time solvable reduction and do a reduction of it to the halting problem. Such a reduction is possible. You can think about how to do it. The halting problem is definitely not solvable in polynomial time. So this is not correct. Y cannot be solved in polynomial time. Well, that might be true, but we don't know that. So it's not this. If Y is hard, then X is also hard. That is also not true, because we know that X is easy, so that doesn't make any sense. And once you delete all the other options, what remains must be true, according to Sherlock Holmes, I think. So, yeah, the correct answer is D. And that's it.